Good morning, chemistry. Our next chapter is on chromatography. And chromatography is a method of separating the components of a mixture that might be difficult to separate from the other methods that you have learnt. So the components of a mixture, like the mixture of coloured inks that make up this purple texture. And you've probably seen this done before. But if you take a piece of filter paper and you get some of the purple ink on the filter paper, like that, and then you put it into a beaker or a wine glass, and you put a solvent in the beaker, water is going to move up the filter paper, up the column of the filter paper, and separate the colours that make up the purple ink. That's what I'm hoping is going to happen anyway. So to understand how it works, the first thing I want to talk about is water going all the way up to the top of the tree against gravity. And the reason, or the way that water can move up into the treetops, part of it, is by something called capillary action, which is about water molecules kind of sticking to parts of the tree and sticking to each other and almost like crawling their way up, just like the water is doing in this glass here, moving its way up the paper. And we'll just watch that, see what happens to that as we go. So capillary action, first of all, there it is the movement of water due to the forces of cohesion, adhesion, and surface tension. So we'll just whack some highlighter on those words: cohesion, adhesion, and surface tension. So cohesion, what does cohesion? Cohesion comes from the word cohesive, and it means holding together. The molecules in water are very cohesive. So the water coheres to itself. The molecules are attracted to each other. They're polar. They like to group together, and they attract to each other. Cohesion is the tendency of water to hold to itself, which I think is what that says, yes. There, cohesion is the tendency of water molecules to stick to other water molecules. And I might just correct that typo right now. Cohesion is the tendency of water molecules to stick to other water molecules. Adhesion comes from the word adhere. So to adhere, like if I put some glue on some paper and I stuck it to, and it would adhere to another sheet of paper. Adhesion is about things sticking together. And the property of adhesion is about the water adhering to a surface. Like if there were drops of water on the window, rather than them just falling straight to the ground, they would roll down the window because they're kind of stuck to the window just a little bit. And that's adhesion. And you might want to write this stuff down. Surface tension is what is created by the fact that water molecules cohere to each other. So the water molecules hold on to each other nice and tight, and that means that they're so busy sticking to each other that they're not going to, something that sits on top is not going to fall through. So if I had some water, I could probably, if it was really, really still, I could balance a paper clip on top, even though the paper clip is more dense and should sink. It will sit on top because of the surface tension, and the surface tension is created by the fact that the water molecules are cohesive. Here's this starting to move. I'm not seeing any separation of colours at the moment, but I am seeing the purple creeping up the page. And we're going to talk about how that works and why that works soon. There's something about surface tension. And if you want to write that down, go for it. Here we go. So you've got a beaker, like this one here, and you put a strip of paper in it. It should actually have a cover over it, and that is to stop the water from evaporating. It's making the water stay in the glass and move up the paper and stop it from evaporating. So with some solvents, you need to have a cover on it. So you put your paper strip in there, you rule a line across the paper strip, especially if you're doing a couple of different tests, a couple of different patches on the table. So we'll just grab a ruler. And you would get a pencil and you rule a line across that page with a pencil. Let's make that a thinner line, shall we? That's a bit nicer. You rule a line across your page. You get a sample of your colour, and you put a blob of your colour on the page. And there's a few words here. There's a few words. Oh, you've got your water level. Your water level, you're drawing there, needs to be, the water needs to be touching the paper, but it needs to be below your start line. I'm going to move that colour dot because it should be on the start line. And the start line is called the origin. And I've got a heap of words over here. I've got some vocabulary for this section. So this start line over here is called the origin. So we'll just do a little arrow there to the origin. Well, that arrow is very heavy. Let's get rid of that and make it thinner. Make it nice and red too. So that pencil line on your page is called the origin. The solvent in the bottom is called the mobile phase, and that's because the solvent moves the way this water is moving up the paper. So the water is called the mobile phase, and the paper is called the stationary phase. Move that over there. Pen, let's line that up. Stationary phase is the paper. The solvent front is where the water is at. Right now the water's there, but as the water moves through, that's a solvent front moving through the water. The solvent front in this glass here is about there, and it's going to just keep moving up. So the solvent front is where the water is. And I'll just draw a little water line. By the end of all this, I'm going to make that grey actually. By the end of all this, we'll have a solvent front up here, and it's where the water has moved to. Chromatogram is the name of the piece of paper that you're producing, the picture that like this picture over here. So this bit here, that's your chromatogram. So I'll put that word down here, and we can put that in a minute. And the components, the color components, I think it's starting to happen in this one here. Actually, I'm going to get rid of that picture, and I'm going to drag this one in. That still works, I think, except for the solvent front. The stationary phase is the paper. So we'll just draw that back in here. The stationary phase is the paper. And the solvent front is the water level, which on this piece of paper is just here. And that's the solvent front. There, chromatogram, and the separation of the components. So the components separate because they move up the paper at different rates. And that's the thing that we're going to be looking at next. I'll just leave that going. I'm hoping to get some colour separation. We've got a little bit of pink there, a little bit of purple. It doesn't look like it's doing very much, but I have a better one for in class. Next page. All right, so as the mobile phase, which is the water, moves along the stationary phase, so as it moves up the paper, the dissolved substances, which is the purple stuff, undergoes a continual process of adsorption. I don't know if you can see that. I'm going to move that out of the way. Move out of the way. Move out of the way. Okay, give up. As the mobile phase moves along the stationary phase, the dissolved substances undergo a continual process of adsorption onto the solid stationary phase, followed by desorption into the mobile phase. So what that means is it adsorbs, it clings onto the paper, and then it gets redissolved back into the water, desorbed back into the mobile phase, and moves up a bit further. And in that way, it kind of sticks to the paper, goes back to the water, moves a bit further, sticks to the paper, goes back to the water, moves a bit further. And different substances are going to be more likely to cling to the paper, and other substances are going to be more likely to stay dissolved in the liquid. And it's got to do with their solubility and their polarity. All right, the rate of movement, there you go, depends on how strongly the components adsorb onto the stationary phase, so how strongly they cling to the paper, and how readily they dissolve in the water. So if they're really quite soluble, they're going to go further, and if they're less soluble, they're going to kind of come out of solution onto the paper early on. And you'll end up with a separation of different colours. I can see a light pink and a dark pink going on here, and I'm hoping it'll get more interesting. I haven't tested out the purple texture, so I'm not sure. So the more soluble components will move further up the column. In your textbook, it says that the thing that moves, the blue dye moves more quickly, indicating that the blue dye is more polar. So it tells you that the thing that moves further up the paper is more polar. And then I looked on Google and it told me that the thing that moves up further up the paper is less polar. And I did some more research, and it actually depends on what your solute is and what the things that are dissolved. But in this case with water, the thing that moves further up is the thing that is the more polar, that's more likely to cling to the water, it's more soluble. Next page. All right. So to find out what is in this, identifying the components. So this is used for stuff like drug testing. You're an Olympic athlete and you want to compete in a sport, you've got to go pee in a jar, and they're going to take that and find out what's dissolved in it. They're going to separate components and see if there's anything that they're looking, any banned substances dissolved in there. And they use this technique, not quite like this, but a similar kind of technique. Finding out what's dissolved in your blood, sometimes for medical reasons and sometimes for drug testing reasons. They can take samples and they can find out what's dissolved in the liquid. You're working for the federal police and you go raid a house and find a bag of white powder and you want to know what it's made of. You can use chromatography to compare what you've found to a known standard, and that's what I've written up here. So identifying the components of a mix, to identify the components of a mixture, you can make a chromatograph of the stuff that you find, and you can compare it to a standard for a known chemical. So you can say, yes, I know that this substance here is, banned steroid number 76 or whatever. And the other way, if you don't have a standard chromatogram for that particular substance, or you're using a different kind of solvent and a different kind of stationary phase, then you can use something called the retardation factor, which is about how much the paper slows the ink down, okay, as the water moves through. So the retardation factor is how much slower your substance moves than the water. Now, in this case, it's moving at exactly the same pace as the water. So I really didn't pick a bad example for this. And it's a percentage. So you go, the water is the total, and how far your substance has gone is a fraction of that. So you get a ruler out, you measure from your start line that you ruled on the paper, you measure to the end of the water. And then for this one, I can see that the colours are starting to separate. I could measure to the top of the pale pink colour, and I could say, well, that's about 50% of the total distance. And if I used a ruler, I could actually give that a proper measurement. So that would have a retardation factor of 0.5. It's always going to be between 0 and 1. And I'm going to hold that up again and see if you can see that the colours are separating. You've got some pale pink, and there's quite a distinct line between the pale pink and the darker purple. It's really hard to see in that picture, but I'm just going to let that go for a bit longer. So see if there's another page. There is no another page. Previous page. All right, so the mobile phase, that's the water, moves along the stationary phase. And the components of your substance will move faster or slower depending on how strongly they adhere to the paper and how readily they dissolve back into the water. So you need, and so there's a few more words I'm going to highlight for you. Adsorption, desorption, those are good words, and the ones from the previous page as well. And then you can identify by comparing your chromatogram to a prepared standard using the same conditions, the same solvent, the same stationary phase, the same mobile phase, the same stationary phase. And or you can use a retardation factor, which means it doesn't matter how long your chromatograph is. If you use a different length piece of paper to me, you can still find that this pale pink has gone about 0.5 of the way along to the water. So it's going to be a number between 0 and 1. All right, I think that's everything.